Okay, so let's learn about how to measure how long an arc of a circle is. So if I have a circle, whoops. If I have a circle of radius r, okay, and I measure off a portion of it, so this segment right here, inside it, that's going to mark off an angle, and we tend to use the Greek letter theta for angles, which just looks like a zero with a horizontal line through it. If you look at the way it's typeset, it's a little bit thinner than a zero, but handwritten, it's tough to do that. Okay, so it's just an oval with a horizontal line, which is very different, by the way, from this symbol. That's very much not the same thing as this. Okay, they are just different symbols. This is a letter that we use to measure angles, usually. This means something else. Don't worry about it for now. Okay, so I have an arc length. I have a portion of the circle. It measures a central angle of theta. Notice they've said a central angle of theta radians. And we'll get to what that means. What does theta radians mean? Okay. Then if this arc length is s, we have this equation s is r theta. Now you can use this to basically define what that term radian means. Okay. So let me clear off the marks so I can talk about what I just said. Suppose you have a circle, its radius is r. Suppose you mark off a bit of this arc length, and using some technique, you manage to measure that this is exactly, well, let's say the radius, let's even specify what the radius is. The radius is 3. And I measure off exactly 5 units of length on the circle. Okay. Then from the center of the circle, this angle, I'll mark with theta. So the radius is 3, the arc length was 5. So what was theta? Well, s equals r theta, so theta is 5/3 radians. So instead of defining the angle as what proportion of a complete rotation was it and arbitrarily deciding that's going to be 360 degrees per circle, we're redefining how we measure angles in a way that's really central to the circle itself. It doesn't rely on our artificial imposition of this number 360. We just say, this length is r. The radius of a circle is a fundamental part of it. Remember, the very definition of a circle is all points whose distance to the center is r. So r is baked into what it means to be a circle. Then what I do is I measure off this angle, and I call it s. And the question is, how many multiples of r was that length? Maybe it was equally long to r, it was 1r. Maybe it was twice as long, so it was 2r. Maybe it was 1.8 times as long, it was 1.8r. In any case, if I mark off the same distance in 2 different places on the circle, they're going to mark off the same angle inside the circle. So this angle inside the circle defines an arc length on the outside. And I can then say, the angle is going to be measured in how many radii it creates on the edge of the circle. So for example, if I draw a circle, now here is my sort of reference of the radius. Now I'm going to draw an arc length, and I'm going to try my best to make it exactly twice as long as the radius. Then I am going to say that this angle is 2 radians, because the arc length it creates is twice as long as the radius. If I make another circle, and I sort of give myself a reference radius here, if I try to draw an arc length that's half as long as the radius, then that angle is 1/2 radian, because it created an arc length half as long as the radius. You're describing an angle based on how much arc length it creates. And you're measuring how many radii of arc length does it create. That is called a radian measure. Okay, so for example, suppose I have a radius 4 circle, and I have a central angle of 0.75 radians. Find the arc length. So we've got a circle, its radius is 4. I have an angle, and I say this is 0.75 radians, then what's this arc length? Well, the arc length is given by the radius times the angular measure measured in radians. And 0.75 is the same thing as 3/4, and now it's easy to see that we get 3. So the arc length is exactly 3. And again, I'm just going to erase my work so that the bookwork shows up. Okay, but there it is. So how do I convert between radian measurement and degree measurement? Okay, so the way we do this is we observe that the complete circle of radius r, if I go all the way around, how much arc length does that create? The circumference, and the circumference of a circle is 2 pi times the radius. So that arc length, 2 pi r, should be the radius times the whole circle measured in radians. We cancel off the r, and we quickly see that going all the way around the circle is exactly 2 pi radians of angular measure. If I divide this by 2, we can see that halfway around is pi radians. So 1 degree, if I now divide both sides by 180, is pi over 180 radians. But if I go back to this formula and I divide both sides by pi, on the right-hand side, we would have 1 radian is 180 over pi degrees. So if you want to convert back and forth between degrees and radians, the key things to remember are all the way around the circle is either 360 degrees or 2 pi radians. From there, halfway around the circle is 180 degrees or pi radians, and this gives me a ratio of pi to 180 or 180 to pi, depending on which direction I'm trying to convert. Okay, so let's practice doing some conversions there. So convert each of these to radians. So for example, okay, the first one I would do 45 degrees, and now I have to do some sort of conversion. How do I know, am I going to do pi over 180 or am I going to do 180 over pi? Well, I just have to remember units. So I want to cancel out degrees, meaning I want to put degrees down in the denominator, and I want to end up with radians. And the 180 is the degrees, and the pi is the radians. Okay. Note when you measure an angle, okay, if you put this symbol up there, you're saying I am measuring it in degrees. If you don't put any symbol there, it is assumed you're measuring in radians. The default way to measure angles from now on is radians. If you don't put the symbol degree up there, I'm going to assume you mean radians. So if you do something, you mark this and you call this 90, I'm going to say no, it is not a 90 radian measure. It's a 90 degree measure. That's fine. Okay, but if you don't put the symbol there, you mean radians. So when you want to write degrees, write the degree symbol. Anyway, back to part A. So now my degrees are going to cancel out. So I get 45 pi over 180. 45 happens to go into 180 exactly 4 times. So this is pi over 4. So a 45-degree angle is a pi over 4 radian angle. And notice I didn't put any sort of symbol on it. If you don't put a symbol on it, you mean radians. So pause the video and try to convert all of the rest of these from degrees into radians, and then we'll double check. Okay, so the first one, as we already did, is pi over 4. All of these, all you have to do is multiply by pi over 180. Okay, so 7 pi over 6 is how part B simplifies. Here is negative pi over 3 for negative 60 degrees. Hopefully you remembered that negative sign. 100 degrees is 5 pi over 9 radians. 109 degrees is about 1.902. The 109 and the 180 don't really simplify. If you had just left it like that, that's fine as well. Okay, how about the other way? Convert these radian measures into degrees. So part A we actually had already basically done in the previous one. So I have pi over 4 radians. I need to multiply it by a conversion factor, but what I want to get out is something in degrees. So do I want 180 over pi, or do I want pi over 180? Well, I want to introduce a degree symbol in the numerator. So I want the 180 degrees per pi radians. And here the pi's are going to cancel, and we end up with 180 over 4, which is exactly 45 degrees. Okay, and this is it's the same angle we did in part A of the last one. So again, pause the video, try to convert the rest of these from radians into degrees, and then we'll check. Okay, so here's the first one. We already did it. Just multiply by 180 over pi, and you get 45 degrees. All of these are now just multiply by 180 over pi. So 7 pi over 6 becomes 210 degrees. Negative pi over 3 becomes negative 60. These are the same angles from the previous example. Now it's different. 5 pi over 2 is 450 degrees. And 2.5 radians, you've got that pi in the denominator now. If you had just left it, as 540 over pi, that would have been fine, which is approximately 143.2. And all of these are measured in degrees, so don't forget your degree symbol. Okay, so here's a word problem. Okay, so for a small angle, the length of the arc subtended is approximately equal to the length of the chord that is subtended. Here's what that means, these geometric terms. So we have a very small angle in, let's presume, a pretty big circle. Okay, this arc length is approximately equal to the length of this straight line. That straight line is called a chord. So as long as, if you had a big angle, by the way, this arc length is very far off from that. But for small angles, it's a very good approximation. So for small angles, you can say the arc length is pretty much the chord length. So use that approximation to judge the field width. In other words, how much scenery the lens can image, so how wide of a view can you get. You have a 400 millimeter camera lens at a distance of 725 feet if the viewing angle is 6 degrees and 9 minutes. So here's what we have. We have a pretty small angle, 6 degrees and 9 minutes. The distance to the target is 725 feet. That's essentially the radius of the circle. Okay? What we want to know is what is the width of the field we can view. And notice that that's now a chord. It's a straight line that connects those 2 points. But we are going to approximate that chord with this arc length. So if I have a circle of radius 725 and an angle of 6 degrees and 9 minutes, can I determine the arc length it creates? Now we have a formula for converting angles and radii into arc lengths, but you need to be measuring the angle in radians. Okay, so that's really what we have to do, convert 6 degrees 9 minutes into radians, and then we can use that formula. So here's a nicer picture. Okay. And as specified, in that formula, we have to have radians, so we convert 6 degrees 9 minutes into radians. So 9 minutes is 0.15 degrees. How would you get that? You would say 9 minutes, but to 1 degree, there are 60 minutes. So I have 9/60ths of a degree. I can cancel a 3 out of that, and I get 3/20ths of a degree, and 3/20ths is 0.15. Okay, so 9 minutes is 0.15 degrees, so we have 6.15 degrees. I multiply by pi over 180 to convert degrees into radians, and I get about 0.107 radians, and now we can just use that arc length formula. Radius times radian angle, 725 feet by 0.107 radians, and get approximately 77 feet. So if you have this pretty small angle of view at a distance of 725 feet, you get about 77.5 feet width view. It's worth pointing out a 400 millimeter camera lens, which is what was described in this example. That's a pretty long lens, and a longer lens. Okay, so the way a lens works is it takes light in the front, and it does a bunch of fancy magic, and it comes back out the back. But basically, it ends up being refracted through something that looks kind of like that. And the back side is always the same size, because that's your camera sensor, or the film if you were using a film camera. So if you have a shorter lens, you get a wider angle. If you have a very, very long lens, you end up with a much narrower angle. So longer lenses give you a narrower cone of vision. Shorter lenses give you a wider cone of vision. Okay. So 400 millimeter lens, that's a pretty long lens. It's really getting into the specialty lens length. And that really means you're zoomed quite in. Okay, you have a very narrow cone of vision, means you're looking at something pretty far away. Okay, anyway, from arc length, we can then move on to talk about areas of sectors. So again, we get this nice formula. It's not so complicated to use, but the angle has to be measured in radians. So if I have a circle, okay, and I have an angle of theta radians, and I want to ask, what's the area of this pi slice? 1/2 r squared theta. So find the area of a sector if the circle has radius 3 and the angle is 45 degrees. Well, we've got this formula. The area is 1/2, it is pi r squared times theta out of 2 pi. The pi's cancel. Sorry, I'm just remembering the formula. Yes, it is r squared theta over 2. Excuse me, times pi. I got the formula. 1/2 r squared. Right, that's it. Okay, sorry about that. So now we have a circle and r is 3, but what's theta? Well, it's 45 degrees, but we need to convert that into radians. So we multiply by pi over 180, and we end up with pi over 4 radians. So the area is going to be the radius squared times the angle measured in radians over 2. And this is going to be 9 pi over 8, which we estimate to 2 decimal places. If this were an exam, just leave it 9 pi over 8, you're fine. You never need a calculator on exams. Okay, so we convert to pi over 4 radians. We use the formula 9 pi over 8, which is approximately 3.53. Let's actually do another example. All right. So let's suppose the radius is unknown. Okay. The angle isn't 45 degrees. It's 28 degrees. And the area is known to be exactly 4 units, 4 square units. What's the radius? Okay, so now I know the area, but I don't know the radius. Again, I have 28 degrees. I need to convert that into radians. So I multiply by pi over 180. I'm just going to estimate that to 2 decimal points. So I'm going to pull out a calculator and say 28 times pi divided by 180 is 0.48. Oh, but to 2 decimal points would be 0.49 radians. Okay, now my formula says my area is pi, sorry, there's no pi in it, I always forget that, is the radius squared, which I don't know, times the angular measure, which is 0.49 radians over 2. So to solve this for r, we multiply both sides by 2. 8 is r squared times 0.49. I divide by 0.49. 8 over 0.49 is r squared, and we can estimate that 8 over 0.49, it's going to be almost exactly 16, is 16.32, 0.33 if I'm doing 2 decimal points, sorry. So 16.33 is approximately r squared. And now I would take plus or minus square root, but of course the radius is not going to be negative. So the square root of 16.33 is going to be very close to 4. And again, rounding to 2 decimal points, the square root of 16.33 is 4.04, almost exactly 4. Whoops, sorry, 4.04. Okay, so you can do a similar problem where you're trying to solve for the radius instead of solving for the area. If you were given the area and the radius, you could solve for the angle, and it would be measured in radians. Okay, sorry, skipping ahead. All right. Now suppose you have a wheel and it's rolling along the ground. Okay. So the radius of the wheel is given by r, and the object is moving at a nice constant rate. Okay. So if s is the distance traveled in time t on the circle, sorry, I should specify what distance. I'm not measuring like how far the wheel rolls horizontally. I'm measuring how far something goes around the circle. So don't imagine like a wheel rolling. Think more like a Ferris wheel. The wheel is in the same place. and you're rotating around the center. So how far do you move at time t? Well, if the speed was v, sorry, if your distance was s and your time was t, then your speed is the ratio. This is just saying that speed is distance per time. So velocity, v, is distance s per time t. Okay. So what is angular speed? Okay, pardon me. All we're doing here is we're saying how much angle do you measure out per time. So it's how fast you're rotating. Okay, this is your RPMs basically. How much angle are you rotating out per time? And that's omega, which typically just gets written by hand and it looks a lot like a W. You can tell when it's typewritten it's a little bit different, but handwritten it just looks like a W. Okay. So this tells me that the velocity is the radius times the angular measure. Okay, because if you solve for this, what we had on the other slide was velocity is distance per time, right? And what we have here is that time is angle divided by angular speed. Okay, and you can plug this in and work through it and actually get this out of that. Okay, let's not worry about why the formulas are justified. We'll just apply them. So suppose you're spinning a rock at the end of a 2-foot rope at 100 revolutions per minute, so 3 times per second. So how fast is the rock moving? What we're assuming here is that when the rock is released, it takes whatever velocity it had, and now it just goes in a straight direction. This is how it actually works. So we need to know how fast it's moving as it goes around the circle, and then when it's released, it will take that speed. So what does this 2 foot tell me? In terms of some sort of circle, it tells me that the radius is 2. 180 revolutions per minute, that's my angular speed, okay? So in 1 minute, I do 180 complete revolutions per 1 minute. So that's my angular speed, okay? So there we have it, 180 revolutions, but each revolution is 2 pi radians. So I'm going 360 pi radians every minute. But if I'm doing 360 pi radians every minute, then how many feet is that? Well, my radius is 2. So I multiply my radius by my angular speed. My radius was 2, and my angular speed was 360 pi radians per minute, which gives me 720 pi feet per minute. If you convert 720 and you just estimate it, it's about 2,200. If you converted that into miles per hour, it's about 25.7 miles per hour. How would you convert this to miles per hour? Well, the minutes is easy. You have 1 minute per, sorry, you have 60 minutes per 1 hour. Okay, so now my minutes are going to cancel minutes, and I'll have hours in the denominator. And I have 1 mile per 5,280 feet. And now my feet cancel. And this is going to give you 22,262 times 60 over 5280 is going to give you your miles per hour. Don't worry so much about unit conversions. You should know how to do it, of course, but it's not really the focus of this course. Okay, so in this section we learned how to measure angles, including, most importantly, how to measure them in radians. And remember, all the way around the circle is 2 pi radians, and from there you get your conversion formulas. To go from degrees to radians, multiply by pi over 180. To go from radians to degrees, multiply by 180 over pi. We also picked up a couple geometric formulas like area of a sector and linear speed and that sort of stuff. The real focus is get used to measuring angles in radian measure, because it's how we're going to do it from this point forward almost all the time. Okay, so that's section 6.1. So guess what comes next?